மாணவர்கள் அனைவருக்கும் வணக்கம். 12th standard physicsல மூணாவது பாடம் Magnetism and magnetic effects of electric current. அதில் இருக்கிற question and answers discussion தான் நம்ம இப்போ பார்க்க போகிறோம். First, I have selected a few questions in 2 marks, then 3 marks and 1 5 mark. So, most of the questions will be from your book bag. So, first let us start 2 marks discussion. 2 marks, there are a lot of questions. First, I have selected define magnetic flux. So, this is a question which is similar to the question which we studied in lesson 1, that is electrostatics. So, now magnetic flux, the number of magnetic lines of force crossing normally through a given area is called magnetic flux, and it is denoted by the letter pi b. It is a scalar quantity and its unit is Weber, and we can write it as Wb, and this is the statement. If you write the statement correctly, they will give you the full marks. But if something goes wrong, that is the normally, magnetic flux, magnetic lines, these words are most important. So, if something goes wrong when you are writing, they will go for the expression which is given for magnetic flux. Magnetic flux pi b is equal to Ba, that is equal to Ba cos theta. So, if the statement is wrong, they will allot a minimum mark for the expression. Then the second question is define magnetic moment. Magnetic dipole moment is also a similar question which is in our first chapter, that is electrostatics. So, magnetic moment is defined as the product of pole strength and magnetic length. So, it is a vector quantity. Now, it is denoted by the letter Pm, that is equal to Qml, and unit is ampere meter square. So, if the definition is wrong, so if the expression is correct, they will give the minimum marks allotted for the expression. Now, the third one is Coulomb's inverse law. Coulomb's inverse law is also a similar one which you can compare and study with electrostatics. So, now what is the statement? The force of attraction or repulsion between two magnetic poles is proportional to the product of their pole strength and inversely proportional to the square of the distance between them. So, this is the statement. So, all the words should be there, and if you miss any word, the mark, you will be missing mark. So, again here also we have an expression, that is Coulomb's inverse law, F is proportional to Qma Qmb divided by r square, and that is equal to mu naught by 4 pi Qma Qmb by r square into r cap. So, this is the expression, and if the statement is wrong, they will give marks for this expression. Then next question is what is magnetic susceptibility? So, magnetic susceptibility, it is a ratio of two physical quantities, and if it is a ratio, the units will cancel, and the magnetic susceptibility do not have unit. So, what is magnetic susceptibility? It is the ratio of the intensity of magnetization to the magnetizing field, and here also we have an expression, that is psi, the letter written is psi m, that is equal to m divided by h. So, this is magnetic susceptibilities expression. Then the next question is what is magnetic permeability? So, magnetic permeability is the ability of the material to allow the passage of magnetic lines of force through it, is known as magnetic permeability. The material will have an ability to permit the number of magnetic lines of force. So, that is permeability. So, here without any expression, the statement is here, and you have to write the statement correctly, and 2 marks will be allotted for this. And the next one is what is meant by hysteresis? Hysteresis, the meaning for the word hysteresis is lagging behind. So, this hysteresis comes under when you study the magnetic properties of materials. So, now the definition is the lagging of magnetic induction behind the cyclic variation in magnetizing field, and it is hysteresis. So, now the meaning is lagging behind. This is also a 2-mark question. Now, the next one is a right hand thumb rule. So, right hand thumb rule, if you hold a current carrying conductor in your right hand, the thumb points in this direction and the thumb will denote show the direction of the current flow. The rest of the fingers encircling the conductor, that gives the direction of the magnetic field lines. So, this is a simple rule which is called right hand thumb rule. So, the thumb gives the direction of current and the fingers encircling or holding the conductor gives you the direction of magnetic field lines. So, the next question is state Ampere's circuital law. Ampere's circuital law, this is a similar law which we studied in first chapter electrostatics, that is Gauss law. So, similar to Gauss law, we have a law here, that is Ampere's circuital law. The line integral of a magnetic field over a closed loop is mu naught times the current enclosed in the loop, and the expression is also given there. So, line integral B dot dl, that is equal to mu naught I enclosed. So, that is the expression. If you write the law correctly, 2 marks will be allotted, and if there is any mistake, they will see the expression, and if the expression is correct, and they will give the mark allotted for that expression. Now, the next question is, now how will you define 1 ampere? So, 1 ampere is defined as that constant current when it is passed through each of the 2 infinitely long parallel straight conductors kept at a distance of 1 meter apart in vacuum or experiences a force of 2 into 10 power minus 7 Newton per meter length of the conductor. So, all the words are important, and the value of force, that is what force is experienced by each conductor, both conductors, that is 2 into 10 power minus 7 Newton per meter, that you have to write the value correctly. So, otherwise the marks will be reduced there. So, this is a condition when you, that is 2 straight conductors and it is separated by 1 meter. From that you are writing this definition. Then the next question is Fleming's left hand rule. So, this Fleming's left hand rule, detail or definition of force, you can find force, the direction of force from this Fleming's left hand rule. So, if we stretch the 3 fingers, that is our thumb, then the forefinger and the middle finger of our left hand. So, stretching mutually perpendicular to each other. Now, our forefinger points in the direction of the magnetic field and our middle finger points in the direction of the current. So, if these are the 2 directions of magnetic field and current, then the thumb will point in the direction of the force. So, all the 3 fingers are mutually perpendicular to each other. The forefinger points in the direction of magnetic field and our middle finger points in the direction of current. If these 2 are like this, then our thumb will be in the direction of force. We will discuss a few 3-mark questions. So, first write the properties of magnets. It is an easy question. So, the properties of magnets, first one, if you suspend a bar magnet, it will always point along the north-south direction. Then the magnet attracts or repels another magnet or magnetic material towards itself. The attraction or attractive or repulsive force is maximum at the ends of the magnet. When a bar magnet is dipped into iron filing, they cling to the ends of the magnet. When a magnet is broken into pieces, each piece behave like a magnet, that is each piece will have a north pole and a south pole. Even if you break into so many pieces, each piece will have a north pole and a south pole. You cannot see a single pole, there no single pole exists. Two poles of a magnet have pole strength equal to one another, that is both the pole strength will be always equal. The length of the magnet is called geometrical length, that is the total length of the magnet is geometrical length, and the length between the two magnetic poles of a bar magnet is called magnetic length. That magnetic pole will be slightly inside the end. So, not exactly at the end, it will not be exactly at the end of the magnet, but slightly placed inside the end. So, the magnetic length will be less than the geometrical length. If we see the ratio between the magnetic length and geometric length, it will be 5/6, that is always the magnetic length will be slightly lesser than the geometric length. So, these are the properties, and it is a 3-mark question. So, there are 5 points, and we can allot like this half mark for 4 points and 1 mark for the last one, or they can ask a question along with this properties of a small 2-mark question along with the properties of magnet. This is the first 3-mark question. The next one is write the applications of hysteresis loop. So, hysteresis we have seen in our 2 marks discussion. The meaning of hysteresis is lagging behind, and from the study of this hysteresis we get so many details, that is information about the magnetic material which we are studying. So, the properties we get, the details we get from this hysteresis is coercivity, retentivity, permeability, susceptibility, energy loss during one cycle of magnetization. So, for each ferromagnetic material. So, we are studying about ferromagnetic material. So, this study will help us to know, that is select certain materials for certain things, that is if we want to select material for permanent magnet, we need certain properties, and these properties can be found, or the knowledge of these properties can be got from hysteresis. So, this hysteresis gives us so many details. So, when we are now it is permanent magnet. Permanent magnets, what are the properties we need for a manufacturer of permanent magnet is the material with high retentivity, high coercivity, and low permeability. These are the properties which we need while manufacturing or producing permanent magnets. So, this we can get from this application, that is hysteresis study. Now, the example is carbon steel and alnico. So, this what is this alnico iron? It is an iron alloy, aluminum, nickel and cobalt. So, this is an alloy. Carbon steel is one material and the other one is alnico. These two have all the 3 properties. The next one is for electromagnet. What are the properties needed to make an electromagnet? That also we get from this hysteresis. The material with high initial permeability. So, initial permeability must be very high, then the retentivity and coercivity must be very less. Then thin hysteresis loop. We have studied the hysteresis loop, a graph. So, the thin hysteresis loop with smaller area. So, this is preferred for electromagnets. So, this for this example is soft iron and mu metal. What is mu metal? We have already studied. Mu metal is nickel iron alloy. It is an alloy. So, that is mu metal and soft iron. So, these are the properties needed when we produce electromagnets. Then core of transformer. So, how to select the material to make a transformer core? The material with high initial permeability. So, similarly as for electromagnet, here also we need high initial permeability, large magnetic induction, magnetic field or magnetic induction, and thin hysteresis loop with smaller area. These are the properties needed when we select material for transformer core. So, the example is soft ion. So, all the properties are similar to the one which we selected in electromagnet. So, the soft ion, we can use the soft ion. So, we have seen 3 applications, that is permanent magnet, electromagnet and core of transformer, that is transformer core. So, 1 mark for each application. So, this is you have to write the example. So, you should not forget to write the example. So, the example carries marks. So, if you miss the example, they will reduce marks for that example. So, we will see the next question. Write the important features of Lorentz force. So, now before writing Lorentz force, features of Lorentz force, what is Lorentz force? When an electric charge, so electric charge is Q, is moving with velocity in the magnetic field B. So, magnetic field is B. So, if a charge with a speed moves in a magnetic field, it will experience a force, and that force is called Lorentz force. A charged particle moving with velocity in a magnetic field will experience a force called Lorentz force. So, we can write the expression. So, the Lorentz force can be denoted by Fm. So, magnetic force. So, Q into V cross B. So, velocity is also a vector quantity and B is also, that is magnetic field is also a vector quantity. So, V cross B, V vector cross B vector. So, this is the vector notation of force. F m vector is equal to Q into V vector cross B vector, that is cross product of velocity and magnetic field. Now, what is the magnitude? Now, we have written in vector form. Now, the magnitude can be written as Fm is equal to Q. So, Vb sin theta, since it is a cross product, Q Vb sin theta. So, that is the expression. So, remembering this expression, we can write what are the features of a Lorentz force. Now, this Lorentz force is denoted by Fm. It is directly proportional to the magnetic field. So, from the expression itself you can write all the other points. So, it is directly proportional to magnetic field, first point. Then Lorentz force is directly proportional to the velocity v of the moving charge. So, the moving charge, the word moving charge is very important. If the charge is not moving, there is no Lorentz force. So, Fm is directly proportional to the velocity v of the moving charge, and Fm, that is Lorentz force, is directly proportional to the sine of the angle between velocity and magnetic field, sine of the angle between velocity and magnetic field, that is sin theta. Fm is directly proportional to the magnitude of the charge q. So, then next one is the direction of Fm is always perpendicular to velocity and magnetic field, that is a cross product of velocity and magnetic field. So, the result of velocity and B is force, and that will be definitely perpendicular to velocity and magnetic field. The direction of Lorentz force on negative charge is opposite to the direction on positive charge, provided all the other factors are identical. That is, if all the factors are identical, then the Lorentz force for negative and positive charge will be in opposite direction. The last point is the velocity of the charge q is along the magnetic field, means then Fm, that is Lorentz force, is 0. So, these are the points, and you will be allotted marks for all these features. So, if you miss any one of the feature, you will be losing mark for that. So, all the points, all the features are important, and you have to write the expression also. Define and explain Biot-Savart law. So, this Biot-Savart law is used to find the magnetic field at a point from the conductor, that is, if a current carrying conductor is placed at a point and the magnetic field to be found, the point where we are interested to find the magnetic field is at a distance r. So, current is flowing in the conductor and we have selected a point within the magnet, that is field, that is point P, and the distance between the conductor and the point is R. Now, in the whole length of the conductor we are taking a small element called dl. So, only due to this dl, what is the magnetic field at the point P? This is what we have to find out initially. So, due to the current element dl, what is the magnetic field at the point P? Then that magnetic field will be dB. Now, what we have to do? So, the magnetic field will be directly proportional to the strength of the current I. Then the next one is the magnetic field will be directly proportional to the magnitude of the length element dl, and it will be also be directly proportional to the sine of the angle between dl and r. So, what is the angle between dl and r? That is theta. So, it will be directly proportional to the sine of the angle between dl and r, that is sin theta. Then it will be inversely proportional to the square of the distance between what? That is the length element dl and the point P. So, now we all the points can be framed together and we can deduce an expression, that is dB is proportional to ideal sin theta divided by r square. So, now we have written proportional to. Now, if you put an equal to sign, you add one constant, that is k, that is k into ideal sin theta divided by r square, and what is that k? The value of k is found as mu naught by 4 pi ideal sin theta divided by r square. So, if this question is asked, that is explain Biot-Savart law, define and explain Biot-Savart law, there are three parts, that is one is the diagram. So, the marks will be allotted for the diagram, then explanation, for explanation part also marks will be allotted, then for this expression, that is 1 or 2 lines. So, they will divide these 3 marks into for diagram they will allot 1 mark, then explanation 1 mark, then for this expression, that is dB is equal to mu naught by 4 pi into ideal sin theta divided by r square, this will be given 1 mark. Now, we will move on to 5 mark question. Now, a common question which is asked very often, give the properties of dia, para and ferromagnetic materials. First, we will start with diamagnetic materials. First property is that is magnetic susceptibility. Magnetic susceptibility is negative for diamagnetic materials. Then relative permeability. Relative permeability is slightly less than unity, and the next one is about magnetic field lines. The magnetic field lines are expelled or repelled by the diamagnetic material when placed in a magnetic field. Then the last one is susceptibility. Susceptibility is independent of temperature. It is temperature independent. So, first one is magnetic susceptibility, then relative permeability, then we talk about the magnetic field lines. It is expelled by the diamagnetic material, then susceptibility. Susceptibility, that is we have studied in our 2 mark question psi. So, it is nearly temperature independent. So, these are the properties of diamagnetic materials. Now, we will see what are the properties of paramagnetic materials. Similar properties are only here it is discussed. Magnetic susceptibility is positive and small. Relative permeability is greater than unity. Here the magnetic field lines are attracted into the material, into the paramagnetic material which is placed in a magnetic field, and the last one is susceptibility is inversely proportional to temperature. The next one is properties of ferromagnetic materials. Now, the similar properties are all discussed here. First one is magnetic susceptibility. Susceptibility is positive for ferromagnetic materials, but positive but larger than the paramagnetic material. Then relative permeability is also larger There we studied relative permeability is greater than unity, but here relative permeability is larger. And here also the magnetic field lines are attracted by the ferromagnetic material when placed in a magnetic field. So, diamagnetic material repels paramagnetic and ferromagnetic material attracts the that is the magnetic field lines into the magnetic field. Then the last one is susceptibility is inversely proportional to temperature. These are the points discussed in this dia, para and ferromagnetic material. It is a 5-mark question. These are all the questions discussed today. I will meet you in another session with some other new questions. Thank you.